Hello, we're in North Carolina A&T. My name is Luis Brown. I'm a computer science major.
My name is Lee Brown, computer engineering major.
My name is Jordan Dickerson and I'm a computer science major.
My name is Gerald Carlson, computer science major.
My name is Noel Davenport, computer engineering and English.
And we were given a task to solve 3 different problems by researching algorithms. Hi, I will be giving you an explanation of the pseudocode for Russian peasant algorithm. Here we have n, y, and nx. Now your while loop will check to see if y mod 2 will equal to 1 or 0. So if it equals to 1, you go down here to your while loop where y is not equal to 0. So if it's 1, then all of your even numbers corresponding to your x and y will be crossed out, and which I will be explaining to you later on in our visual. And here we will be adding all of the corresponding y odd numbers to your x numbers, which means all the numbers that have not been crossed out. We will add those numbers to your total sum, but will give you the sum of these 2 integers multiplied together. Hi, now I will be explaining the time complexity for the Russian peasant and Egyptian algorithm. Now let's say we wanted to plug in n of 100 into the log of n for the Russian peasant. When plugging in 100 into the log function, this equals to 2. Now when plugging in 100 to 2 log of n, we already know that log of 100 is 2. So 2 times 2 gives you 4. So as you can see, the Russian peasant will be the fastest algorithm to use. Hi, this is the pseudocode for the Egyptian algorithm. And the first while loop is creating a table with its values. And then the second while loop is basically going to take the sum of the values. And I will be showing you that in a real life example. Now I'll be giving you an example of the Russian peasant algorithm. Now let's say we have 57 and 86. According to our pseudocode, we had to modify the y value to see if we can get a 1 or a 0. If it's a 1, which is not equal to 0, it will be odd. So by this, what we'll be doing is halving all the y values until we get to 1. And then we will be adding 57 plus 57, which give you 114. And then we add each individual number until the number on the left side corresponds to the number on the right side, which will be 1, where we'll be ending at. Then we'll be crossing out all of the even numbers, and which we will be crossing out the entire row. Then we will add all of the numbers on the first column, which will then give us 4902, which is the answer when you multiply 57 times 86.
My name is Lee Brown and I'll be explaining the division algorithm. In the division algorithm, A is our dividend and B is our divisor and Q is our quotient. In this algorithm, you divide A by B and you also use Q as your counter, while making sure that B is less than A. Your new A will always be A minus B, and your counter will always be equal to Q plus 1. While we use R as our remainder, which is left over from A, and we always return Q and we always return R, which is our remainder. This is how a division algorithm works with real life integers, with A being equal to 29 and B being equal to 7. And you would use A equals A minus B as your equation. And again, with A being equal to 29 and B equal to 7, you would have A equals 29 minus 7 equals 22, which would be your new A. And then you compare your new A to your B to make sure that A is greater than 7. And that would be your first count. And then you would take your new A and reapply into your equation, which is A minus B, to get A equals 22 minus 7. And your new A would be 15. And again, you would compare your new A to your B. And that will bring you to your second count. And you would again reapply your new A to become your current A in your equation, which would now be A equals 15 minus 7 equals 8. And again, you compare your A to your B, and you get your third count. After reapplying your new A into your equation, you would have A equals 8 minus 7 equals 1. And then you compare your new A, which is 1, to make sure that it is larger than your B, which is 7. And you would get your new count, which is 4. Since 1 is not larger than 7, then 1 will be your remainder. And to check your algorithm, you could also apply A equals Q, which is your count, times B, which is one of your integers, plus your remainder. And you would have 29 equals 4 times 7 plus 1, which equals 29.
Hello, I will be going over the pseudocode for Euclidean division. If x is equal to 0, then the quotient and remainder will be returned as 0. If not, I will do x divided by 2 and apply flooring. So 6 divided by 2 is 3, and I have y equals 3. I will then apply the grouping function to these numbers. Think of the grouping function as sorting a bag of marbles. Let's say I have A, 3 marbles. I want to group them into B groups of 3. So here I have 1, 2, 3 marbles in one group of 3 with a remainder of 0. So I'll then apply these numbers to the following two functions. Q is equal to 2 times Q. So that's 2 times 1 equals 2. R equals 2 times R. So that's 2 times the remainder of 0 equals 0. If x is odd, then I will do R equals R plus 1. However, x is not odd. If R is greater than or equal to y, I will do R equals R minus y. And Q equals Q plus 1. However, R is not greater than or equal to y. So I will then return Q and R, Q being my quotient of 2 with a remainder of 0. I will now go into a more in-depth visual example of how to apply Euclidean division. Here I have a bag of 13 marbles. Let's say I'm doing 13 divided by 4. I will group my marbles into groups of 4 until I can no longer have a complete group. So here I have one group of 4, 2 groups of 4, 3 groups of 4, 4 groups of 4. So it's 4 groups of 4, and I have one left over, which is my remainder. This is how the Euclidean division algorithm is applied.
Hello again, and we're here to explain the time complexity of problem number 2. For the division algorithm, the time complexity is big O of n.
The time complexity for the Euclidean division algorithm is big O log of n.
If n is equal to 100, then the time complexity of the division algorithm would be equal to 100.
And the time complexity of my algorithm will be 2.
Since the Euclidean division algorithm's time complexity is smaller than the division algorithm, then that means the Euclidean division algorithm's running time is faster.
Hi, my name is Davenport, and I'll be explaining the recursive power algorithm. For this type of algorithm, we're taking x and multiplying it to the power of n, and both integers are greater than 0. There's 3 separate cases in this algorithm covering the basis for different types of integers. If n equals 1, then it's return x, because anything to the power of 1 equals x. If n is even, then we apply this function recursively, and then we have our x, and then we have n divided by 2. And we set that equal to y. After that, we then return y times y. The last case is when we set y equal to this function, however we change it because n is no longer even. So now we have x, then we have n minus 1 divided by 2. And our result is returning y times x. And now we're going to apply the recursive algorithm to an actual example. And we're going to use 6 for x and 7 for n, and we're going to replicate 6 to the 7th. If we refer back to the pseudocode, we have 3 different cases for our n, or what our exponent is going to be. If n is equal to 1, we just return x, because anything to the first power is itself. We check if n is even. In this case, 7 is n, so that we skip that case and move right to the last case. So our n is odd, so then we apply this line of our algorithm. As you can see here, we also need to calculate our n minus 1 divided by 2. Here, our n is 7. So we apply 7 minus 1, which is 6, divide that by 2, and get our 3. Then we try to find y recursively. Y is equal to x to our n minus 1 divided by 2, which we got that to equal 3. So essentially we're doing x to the 3rd power, but the algorithm does this using multiplication. So we literally have x times x times x, which is 6 times 6 times 6, which is 216. Then for our return statement to get our answer, we have return y times x. The reason doing so is when you're multiplying things with exponents, you add them together. So here, we're adding. So our exponent was n minus 1 over 2, and we got that to be 3. If you add the exponents from each of these y's, you had 3 plus 3, and originally our x is by itself, so you have 1, and that is going to equal your 7. The reason you can check this is by using this algorithm. If these two numbers do not match, if your n does not match the number of exponents when you add them together, then you have done this algorithm incorrectly. Since the numbers do match, we can then come down and sub in numbers for our y and x. Our y we got to be 216, and our x is originally 6. 216 times 216 times another 6 equals 279,936. And that is your answer.
I'm Jordan Dickinson, and I'll be explaining the exponentiation by squaring algorithm. First, we have a method with n power, and it takes in x and n. We have n result, and it's equal to 1. Then we start with a while loop, and it says while n is not equal to 0, it's going to run. And this if statement actually checks to see if the number is even or odd. If n equals 2, it will go through the method. If it's odd, it will go through this method. Result times result. Result equals result times x. And it will take n and subtract it by 1. And then it will end that method. And we'll have x down here multiplied by itself to get a new x. And we will then divide n by 2 to get n and end the code. We will now try to find out which of the two algorithms we found have the fastest time complexity between the recursive power and the exponentiation by x squaring for problem number 3.
For my algorithm, the time complexity was big O log of n.
And for mine, I have the same as big O log n.
Now, of course, if the time complexities are the same, whatever value you put in for n, they're going to equal each other. However, our reason for referring to this algorithm as the best is because in our pseudocode, my algorithm actually uses recursion to solve the problems. So instead of doing each individual step, the algorithm is actually doing multi-steps within itself to solve things quicker.
Hello again. I'll be explaining the exponentiation by squaring algorithm. And to start off, we're going to be trying to find 6 to the 7th power. So we start off with assigning x to 6, n to 7, and our result by default will always be 1. So we start with the loop. 7 is not equal to 0. And this method right here, this part of the code right here is to check to see if the number n is even or odd. Since 7 is odd, we'll do these 2 steps. We'll multiply 6 x times the result 1 and get 6 as our new result. And we will also subtract n7 minus 1 to get 6 as our new n. Then we'll move down and multiply 6 by itself to get 36 as our new x. And then divide n, which was 6, by 2 to get 3 as our new n. And we'll loop and start the whole process over again. And we see that 3 also is an odd number. Since it's an odd number, we'll do the 2 steps again by multiplying 6 times 36 to get 216 as our new result. Then we'll subtract 3 minus 1 and get 2 as our new n. And we'll multiply 36 by itself to get 1296 as our new x. And then we'll divide 2 by itself to get 1 as a new n. And again, 1 is odd, so we'll repeat the steps. And we'll get 216 times 1296, and we'll get 279,936 as our new result. And once we subtract 1 by itself, we'll get 0. And since it's 0, it will not loop around again to give you a new result. So we have our answer right here as 279,936.